Hi, I want to take a look at how we can calculate the maximum safe displacement for a mass that's sitting on a second mass where the second mass is connected to a spring, it's free to oscillate back and forth, and there's only friction connecting the two masses. We're going to assume that there isn't any friction between the bottom mass and the ground, though, to make our lives a bit easier. So the coefficient of friction between the masses, we're told, is 0.4. The top mass has a mass of 1 kilogram. The bottom mass has a mass of 10 kilograms. And as long as our spring is hooked up to the bottom mass, it turns out it doesn't matter which one is which. We'll see that in just a little bit. Our spring has a spring constant or spring rate of 400 newtons per meter. So as long as those two objects stay stuck together, we could treat it like it was a single mass hooked up on a spring. Now, if we wanted to take a closer look at the force picture for each individual object, for object 1, in the direction of the acceleration, if our displacement is initially to the right, our acceleration will be to the left because the force of static friction is there to push that object to the left. Now, the second mass is going to feel the spring force pulling in the direction of the acceleration, but then that force of static friction pushing against it. And as long as there's no relative motion between the two, we could just sum that picture together and that static friction would cancel out. Now, the one thing we do need to know looking at this individual picture is that as long as this object is horizontal and level and its top is flat and there's nothing else acting on that first mass, then the normal force between those two masses should be the same as the weight of the mass on top. So our maximum force of static friction we're going to deal with is going to be the coefficient of static friction times mass 1 times the strength of gravity. And as they're stuck together, we would expect a natural frequency omega that would be the square root of the spring constant divided by the total mass that's going to be in motion. Now, for an oscillating system, our maximum acceleration happens when we get our maximum force. So if I look at mass 1, the maximum force I get is the maximum force of static friction. Mu naught times mass 1 times gravity. So the maximum acceleration is my maximum force divided by mass 1. Mass 1 cancels out, as I said. So we'd be left with a maximum acceleration of the coefficient of static friction times gravity. From kinematics, for an object in oscillating motion, our maximum acceleration happens at our amplitude times our natural frequency omega squared. Now, we aren't told an amplitude. We want to figure how far back we can pull and still be okay. So really, we're looking for the maximum amplitude there. And that maximum amplitude is the coefficient of friction times gravity divided by the natural frequency omega squared. And omega squared is our spring constant k divided by the total mass. So dividing by that means we'd have our coefficient of friction times gravity times our total mass divided by our coefficient of static friction. Sorry, that's our coefficient of static friction, that's our spring constant. So, we take a look at the amplitude. We have 0.4 for the spring constant, for the coefficient of static friction, I did it again. 9.80 meters per second squared is the strength of gravity. 11 kilograms is our total mass. 400 newtons per meter as the spring constant. So dividing that out, it gives me a maximum amplitude of 0.216 meters, which would be 21.6 centimeters. Thanks for watching.